All right, I'm back. I'm back for round number 2. Round number 2 is going to involve the problem we were just talking about, but now we have to talk about modeling rotational kinetic energy. I know I have rotational momentum to go to. I haven't forgotten about it. It doesn't necessarily matter in which order I do it, but for now, since I did that last lesson, and the last lesson again was the puck rolling down a ramp, and we were trying to derive a formula for the linear acceleration for the puck in terms of the rate at which its speed increases as it goes down translationally, and we got a result of 2/3 g sine theta. Well, g is 10, 9.8. 10. They're going to want you to use 10 on the AP exam. 2/3 is 66%, 6.66 out of 10, right? And then sine theta. It was a 30-degree angle that in my ramp example. Sine 30 is a half. So that means the sine 30 is the number 0.5. We're just thinking through. 2/3 g sine theta. 2/3 times 10 is 6.66. That's the 2/3 g. And then the sine theta is a half because it was a 30-degree angle. So a half of 6.66 is 3.33 meters per second squared. So, I mean, it tells us if it were to roll for 1 second, its linear speed would be 3.33 meters per second. V equals AT, right? Linear graph, constant acceleration. After 2 seconds, its instantaneous speed at 2 seconds would be 6.66 meters per second. 9.99 meters per second after 3 seconds. Now, what we're going to do is return to that image and talk about, again, modeling the rotational energy. Rotational energy. Just make sure I am recording, I am presenting. Yes to both. So this is where we were at in the last video. I mean, I erased some stuff, and this was the result. 2/3 g sine theta. All right. So let's see how we can use this in more of a discussion about rotational energy and how rotational energy kind of comes back and fits into the concept of total mechanical energy. It certainly is a mechanical energy. It's a kinetic energy. Any type of kinetic energy is a mechanical energy. And there's actually 3 types. There's actually rotational kinetic energy. Take a moment to return this to its home, temporary home. It has a couple homes. Let me just check to make sure that that angle is proper. Not really. Oh, come on. That's a little better. All right. There is 3 types of energy. Kinetic energy is rotational kinetic energy. There's vibrational energy, which means something's kind of vibrating in and out, like my spring here. If this was kind of going, that's like a vibrational energy. Rotational would mean it's rotating, right? And then translational means it's moving. Got rotational, got translational, we have vibrational. Now you can try to do all of them at the same time because it's fun. There we go. I know, you want to see it again. There we go. And notice what I'm doing, right? This is the vibrational part, rotating, and I'm moving sideways. Translational, vibrational, and rotational. So if someone says, what is the total kinetic energy he had? I'd have to add them all together because they're all forms of kinetic energy. Vibrational usually is spoken of in chemistry because atoms are able to have all three types of energy. The vibrational one is usually pretty significant. That's why steam can burn so badly. The water molecules, after evaporation, have a significant amount of vibration after they snap free from their bonded friends. Boom, they snap off and then they just vibrate and they rotate and they move in straight lines. But that vibrational one is a significant amount of energy, which is why the burns can be so bad from steam. Anyways, returning to this discussion, which I promised we would do. Just going to put that a little higher. And let's just use the result to move forward. So let's just say this was still the same 30 degrees, and this was the same disk, let's just say. And we now know that it's accelerating downward at a rate of, not g sine theta, so sorry, 2/3 g sine theta in an example. Well, if that's true, even though we know it's rolling, right, we know it's going to roll, it still has a translational motion and it still covers some physical distance along the ramp each second, and therefore it still has some linear speed v, right? So let's just start with wondering, like, how would we find v final when it passes this point here? Or how would we get omega at this point here? Or how would we get the rotational kinetic energy, which would be translational or rotational? These are all things we can kind of think about. Notice that we have some linear mentions of v final and kinetic energy, good old 1/2 mv squared, but we also have mentions of the rotation world, omega f, how rapidly it's rotating at the end of the hill, the ramp, and the rotational kinetic energy. Remember, we still have v final equals at. Technically, we have v final equals v initial plus at, but as a lot of problems are, the initial velocity is 0, and the linear velocity increases linearly. That's v final versus t graph, kind of a little kooky, but it is. Remember, the slope is a. It's like in the form of y. V final is like y. T is like x. T is on the x-axis. V final is on the y-axis. So a is slope. Y equals mx. It's a key thing that you need to be able to do. It doesn't really matter what it is, right? If it's, they decide to put f versus a, well, what is the graph going to look like? Well, it's going to be linear. So these are all in the form of y equals mx. What would the slope be? What would be m? If they decided to put momentum on this graph, on this axis, and v here, what would it look like? It'd be linear, because momentum is proportional to v, just like force net. This would really be net force proportional to a. What would the slope be? It would be the mass. What if they decided to put, anything? It doesn't really matter. Any of the formulas that are something equals something times something. There's many of them. Certainly quite a few, right? Even if it's like the work energy theorem, or or I could say impulse. Impulse is F, delta T. Well, that means if I put T on this axis and I on this axis, and they talk about an experiment where each time the delta T increases and the impulse increases, then F is the slope. Just point that out. Also, another one is the slope of any energy, potential energy graph is F, the force. Like we can do it could be any distance. Slope is F. Is the force that's actually causing the potential energy to change. So we could use certainly mgh as an example there. And if we take away distance and just put h, and we're just assuming that something is being lifted to higher and higher heights, and each time it gets lifted to a higher height, we know that it has more and more potential energy. Not surprisingly, that's linear, because potential energy is proportional to h. And therefore, that's not a really good line, but it would be linear. And then what would the slope be? Well, if this is on the y-axis, this is on the x-axis, and the remaining bit must be the slope, m for slope. Take away m, it's confusing. So that means the slope of this graph is mg, but mg is actually the force. Right? As you lift something up to higher and higher heights, at any given height, the force of gravity that pulls it down at that height is mg. It's constant. It doesn't matter whether it's 2 feet off the ground or 20 feet off the ground. That's why it's a slope, because the slope is constant. So that's just another awareness for you to have. Just that general idea about graphing, and that for this one, potential energy, any potential energy versus distance graph, the slope is the force at that particular position, but actually it's, at least for that case, since it's linear, it's constant. That wouldn't necessarily, I'll point out, that wouldn't necessarily be true if we were looking at two planets that are far apart like this. The potential energy of two planets that are far apart is gm1 m2 over r, where r is the distance between the two planets. So in that case, the potential energy is inversely proportional to r. That graph would look like this. That's what an inversely proportional graph looks like. If they graphed the potential energy of these two planets as a function of r, meaning if they got further and further apart, you moved them further and further apart. In fact, yeah, did that. I realized I made a mistake. This is one of those weird examples. It's not quite right. There's a negative in front of that, so it's actually, sorry, this is one of those unusual formulas that has a negative in front of it. So actually, what happened? It's negative gmm over r squared. So it actually would go like this. And so at larger and larger distances r, the potential energy would keep going, up higher and higher and higher, because they have more potential to fall towards each other and have all that potential energy turn into kinetic energy. So two planets much further apart, just like a basketball way higher in the air has more potential energy, it's further from Earth. Anything further from another object has more potential energy. That's why this is an increasing graph. However, the slope of this would still be the gravity force between them, because it's still a potential energy versus distance graph. The slope is the gravity force, which is not the same everywhere. Right down here, it's a very low slope. So that means when they're close together, r is small because they're close. The force between them would be small, and then greater and greater and greater, it would be the opposite direction. Although, yeah. Well, just know that the graph part and that force is the slope of any potential energy versus distance graph. All right. And I'm doing all those things just to we're only a couple weeks away from the AP exam, right? So I'm trying to fit in some review things. So if we return to this, if we wanted to get the speed of this ball at the bottom, again, I know 2/3, I'm just going to use G as 10. And since this was sine of 30, then we end up with 2/3. Then we end up with 2/3 times 10, which is 6.66. And then sine of 30 is a half. So we end up with 3.33 meters per second squared. So that would be the linear acceleration of this thing, the linear acceleration. So let's just say, it rolls down for 2 seconds. So we hold it up there, we release it, and we're wondering, 2 seconds later, let's get some information about the 2-second mark. be final, like I had all these question marks. Let's assume it's 2 seconds later. All right, so the acceleration is 3.33 and the time is 2. So I guess its speed at that moment would be 6.66 meters per second, assuming it's 2 seconds, right? And then I could even say, well, what would the length of this ramp have to be so that it went from the top of the ramp exactly to the bottom of the ramp in exactly 2 seconds? That's a distance versus time in connection with acceleration. So if 2 seconds was my random choice I made here, acceleration we said was here, 3.33. In fact, yeah, sorry. So I end up with 3.33 divided by 2. Well, that's 4 divided by 2, right? So that's just 6.66. So if this ramp, I'm just making this up. Let's just say this ramp is 6.66 meters long. Because if it is 6.66 meters and we release that thing in exactly 2 seconds, it'll be at the bottom of the ramp because that's just how I just made this problem. It'll be right there at the 2-second mark. Right? Okay, so if we have the speed, which we did on the bottom at 2 seconds, how could we get omega at the 2-second mark? Well, what's the connection? What's the link between linear world and rotational world for V and omega and A for alpha? You need to know them. V equals R omega and A equals R alpha. So if we know the linear speed of any rolling object and we're asked what is its rotational speed, V, it's just V equals R omega. So I guess I'm going to have to pick an R, which I haven't done yet. So let's put an R in here, and let's just say R is a half a meter, 50 centimeters. That's big. This is a big ball or a big disc. Whatever, doesn't really matter. So let's just say R is 0.5. In fact, if I'm solving for omega, why don't I just write this for omega? Omega will be V, the tangential speed, divided by R. Well, again, we just call it tangential just because as the ball rolls, and if it was a little rock, I don't know, that was embedded in the thing that's rolling. He does that. The speed is tangent. The velocity vector for that little point is tangent to the circle. All right, so I have the speed was 6.66. I decided to say the radius was going to be a half. That's the same thing as multiplying by 2. So that should give me 12 and then 1.2, 1.32, 13.32. And that would be radians per second. Right, so that tells me the rotational speed, the instantaneous rotational speed of this rotating sphere when it reaches the bottom, or not sphere, sorry, rotating disk is that amount, 13.32 radians per second. How would I then figure out how much rotational kinetic energy it has? And I didn't do the other part. I guess I could do the other part. If we were doing the translational kinetic energy, of course, it's just 1/2 mv squared. I never gave a mass to this, did I? Guess I have to. All these things I have to make up. Let's just make it 1 kg, just for fun, just for make it easy. Let me make this a 1 kilogram disk. It shouldn't really matter. All right, what is V? V at the bottom, because we're talking about the bottom, we said was 6.66. That's what we were just using just a moment ago, 6.66. Right? So I'm going to do 6.66 squared divided by 2. I get 22.17 joules, right? So I know there's a little over 22 joules of translational kinetic energy as it slides in the linear line down the ramp. And at the bottom of the ramp. The bottom ramp, it has that amount, 22 joules of kinetic energy, which means whatever the potential energy is at the top, I don't know, I haven't calculated it yet, but if it was 100 joules, again, of potential energy at the top, then the difference, 78 or so, must be rotational. That's the idea, that the potential energy turns into those two other forms, right? So if I wanted to now get the rotational kinetic energy, it's 1/2. Again, we just come back to the formula. M is like I, they're both inertia terms, and V is like omega. So technically, I for a disk is I for a disk is 1/2 mr squared. And so in here, I would place in for I 1/2 mr squared, in for I here. And then in for omega, I'll ultimately have to stick in whatever omega is and square it. Sure, that would be great. Hey, thank you. I'll take free food. I never turn down free food. Yeah. Hey, thank you. Appreciate that. So the mass I had made 1 kg, and the radius back over here, I'd make these things. Radius was 0.5 squared, and then omega. Thank you. Have a good break. And then omega. What was omega? Oh yeah, it's down here in the bottom right. 13.32. This is just how you do it. This is how you would calculate the rotational kinetic energy of something. It's 1/2 I omega squared. I, again, isn't just like M. M is like 2 kilograms sticking 2. Well, for I, you have to calculate it. It's more of a pain. Just the way it is, right? So I end up with 1/4 mr squared omega. All checks out, all right? So let's see, 13.32, clear. 13.32 squared times 0.5 squared, and all divided by 4. I get 11.09. So that means if I have the rotational kinetic energy, that's what this is. And if I have the linear kinetic energy over here, or translational, they usually call it linear kinetic energy, then at the bottom of the ramp, what is the total mechanical energy? 22 plus 11, about 33 joules, right? Because there's no potential energy left. It's at the bottom of the ramp. So now let's start talking about the total mechanical energy. It's all part of the lesson. Total mechanical energy of the Earth disk system. I know. You know, I love it. I love it. Apparently, again, at the top of the ramp, if they say, what is the total mechanical energy of the disk? You're supposed to say 0. If it's not moving yet, and you just mentioned the disk, a disk can't have potential energy. Only the disk and the Earth can have potential energy because it takes two things to fall towards each other to have potential energy, right? That's their little trick. Just the disk has no mechanical energy at the top. If they say the disk Earth system at the top, then it's potential energy, MGH, right? We're going to play along. At the top, what would it be? Top of the ramp, it would be potential energy, right? MGH. Now what, I'll just model it first, and then we'll check out some numbers to see if it all checks out. I mean, I hope it does. It should. At the bottom, it's kinetic energy rotational plus kinetic energy translational, right? So that's how we would just model that. It's the sum of the two types of kinetic energy. I have to start erasing stuff for sure. I'm going to erase on this. I'm going to erase all this. This, again, was the rotational amount. I'm just taking note of it down here. And then the linear translational is 22.17 joules. That's a J, sorry. Okay. All right. So technically, the conservation of energy should work. It has to, right? It should. Right. The total energy at the top of the ramp, total mechanical energy, between the Earth and the disk, should be equal to the total energy at the bottom. How would we express that? Potential energy at the top should be equal to the rotational kinetic energy plus the translational kinetic energy. If we wanted to keep re-expressing with more detail, MGH should be equal to 1/2 I omega squared plus 1/2 M squared. Full points, if that's what they said. Just write down a formula that models the conservation of energy. And they do. That's a very common thing. It's less common that they actually ask you to make the calculation on a free response question. This is it. The total energy that it started with, which might be 100 joules, well, actually it can't be 100 joules. It has to be 33, right? If we know the right side of the formula is suggesting that the translational and rotational energies in total, kinetic energy-wise, is 33, give or take, then MGH must be 33. It has to be. Let's see if it will come out that way. It'll be a jump for joy if it does. I hope so. I mean, I can't make any promises. Sometimes, one little mistake that I make, and I make mistakes sometimes. If I did make no mistakes, MGH should be, in fact, 33.26 joules. Let's check. We know that the length of the ramp is 6.66 meters. We know that this was a 30-degree ramp. I should be able to determine the height. Since the height is opposite to this angle, the height should be the hypotenuse, 6.66, times the sine of the angle. Since the angle is 30 degrees, and we have to have this skill, at least I recommend it. I take that back because I later remember that they actually give you the chart for this on the AP equation sheet, but I still suggest that you have this skill. 60, 30, it's 1, 2, and root 3. 1's the smallest length, 2's the longest length, root 3. Sine 30, here's our 30. Opposite over hypotenuse. Opposite is 1, hypotenuse is 2. So it's 1/2, right? So since sine of 30 is 1/2, then really the height should be half of 6.6, which is 3.3. Right? If I know the height, then I should be able to do MGH and pray that it comes out as 33.26. Let's try MGH. What was the mass? I gotta stick with whatever I picked. I picked mass of 1. We used G, which was 10. Right? That's what I used, didn't I? Yeah, I did. And then our height, which we just trigonometrically worked out as 3.33. Oh, I'm feeling good right now. I am feeling good about this. I am. And the reason why is because I know 1 times 10 is 10, and I know 10 times 3.33 is 33.3 joules. And when we compare that to the total that's over here, oh, that's nice. Oh, that's a victory for physics. It is a victory for physics. I mean, it's not exact, but it's pretty darn close, right? The total over here was 33.26 joules of total kinetic energy at the bottom of the ramp, or total mechanical energy at the bottom of the ramp. And when we figure out what MGH is from the beginning, it's 33.3. That is a victory for physics. So at least you see how that all works. In the previous lesson, again, I did describe and show how you can actually determine what the linear acceleration of an object is that's rolling down a ramp. You end up having to use Newton's second law in the linear world. And on the next side of the screen or side of the page, you do the rotational stuff with torque and rotational inertia and alpha. Then you make some substitutions into your rotational world, like A in for alpha, A over R for alpha, and you solve for friction force expression there. You don't have to use the mu. And then you sub it into the linear world. This was, again, the last lesson, into Newton's second law written for linear motion, which was mg sine theta minus ff equals ma. And then when you plug that in, you can get the solve for A pretty quickly, just a couple steps, and it comes out to 2/3 g sine theta, right? Then in this lesson, we've used how do we actually, fold the discussion of energy into it. If the acceleration was 2/3 g sine theta into the same lab, and I've shown you, it can be used to figure out what the linear speed is. We knew that from September or October, probably September. Reminding you that we can use V equals R omega. So if you know the linear speed at any given moment, just use V equals R omega. If you know V at any moment and you know R is always R, then you can calculate omega at any moment. As soon as you know omega at any moment, in this particular case, it was the bottom of the ramp, then you could actually work out what the kinetic energy is, the rotational kinetic energy, I omega squared. I is easy. For the disk, it was 1/2 mr squared. That's an easy calculation. Once you have the kinetic energy, rotational kinetic energy, you can work out what the translational kinetic energy, 1/2 mv squared. We know how to get V. We just said how to get V, right? Once you have the acceleration, you're just using A times T to get the velocity at the end of the ramp. And once you've got V over here, technically you can work out again the linear translational energy, and then you got both. You can add them together. If they ask you again to express the whole thing, that models this idea that the total mechanical energy of the Earth disk system of MGH transforms or converts into these two types will often get you a lot of points on those free response questions. All right, I think that pretty much covers what I wanted to cover today, for sure. Actually, there's one last thing. It's really quick. I know you're thinking, oh my God, he's still going to go. No, just one last thing. If somebody asked, it literally takes 2 seconds. If they ask, what is the angular momentum of this disk when it's at the bottom of the ramp? It's just I times omega. It's a nice, easy calculation. If you know I, which was 1/2 mr squared for this disk problem, and you know omega at the bottom of the ramp, and we've just talked about that, is V equals R omega, to go from the linear V to the rotational omega by just using that connection, V equals R omega. Then you multiplying them together gets you the angular or rotational momentum. That's an easy calculation. If they ask what it is at any point along the ramp, omega is a function of time, right? Because V is a function of time, right? V is a function of time. Omega is a function of V. It's a composite function. I mean, if you want to call it that from like math stuff. F of G of T, I think, is right. F of G of T. F of T and G of T. F of G of T. Like a song. The bottom line is, since the speed depends on time, obviously how long it's been rolling affects how much speed it has, and it's a function of time. And therefore, as soon as you know AT, it just plugs in. So it's really IAT. I mean, technically, right? You plugged in AT in for omega. I don't know if I'm saying that right. Sorry, I might be saying that wrong. Yeah, I am saying that wrong. You'd end up having to use both of those. Omega is V over R. V is your function of time. And since V as a function of time is A times T, technically this would get erased and you'd put A times T here. And that would go there. Technically, right? And then you be able to say that angular momentum as a function of time is the rotational inertia I times AT over R. I mean, that's just me just creating that, but just pointing out it's all something you can think about, and they might very well, wrap that in there. If they wouldn't have you probably express it in terms of those things, but they certainly would ask you to, think about L equals I omega and comments about, is the angular momentum increasing as this thing goes down the ramp? Well, it's gaining rotational speed. It's gaining linear speed. It has to be, right? It has to be gaining momentum. How about the mechanical energy? Did the total mechanical energy change as it went down the ramp? No, because this wasn't sliding. This was rolling. Very, very little heat is created when something is rolling. That's why things roll forever. You roll a bowling ball in this school and this tile floor, it goes, keep going, keep going forever. Yet when you slide something, it almost immediately stops because of the frictional effect, turning that energy into heat. So as this thing rolls down the ramp, the potential energy is decreasing. The kinetic energy in both cases is increasing because all the potential energy is just dumping into two buckets, translational and rotational. So both kinetic energies are increasing as it goes down. The total mechanical energy stays constant. It's the one common thing that kids get wrong, because that's conservation of energy, unless, again, there's a frictional effect and heat is being lost to the environment through the frictional effect. Then if the system is defined as to not include the air, then it's not constant. Total mechanical energy would be decreasing because it's losing some of that energy to the air. But kinetic energy increases as it goes down. Potential energy also decreases as it goes down the ramp. Total mechanical energy stays the same. V increases, omega increases, angular momentum increases. All right. I'm done for today. I think I am. I think I'm done for today. All right, guys. I'll see you later. Bye-bye.